So here we're just looking at digestion and absorption for carbohydrates. We are done with digestion. Now we're interested in absorption of carbohydrate monomers. So these monomers, mainly we have three types of carbohydrate monomers: glucose, galactose, and fructose. So once the digestion of carbohydrates is done, how are these monomers internalized by the enterocytes? So I have told you to say that on the apical side of the cells, we have sodium glucose transporter 1 that is responsible to transport sodium with a glucose or sodium with a galactose. So this is a co-transporter. It's involved in secondary active transport. So the absorption of sodium and glucose is by secondary active transport. Then they will be internalized by the enterocytes. So now the sodium and the glucose and galactose is within the cells. How do they move to the other side? They are going to use GLUT2 channels. So the GLUT2 channels are facilitating the diffusion of glucose, galactose, and fructose. So be it glucose, galactose, or fructose, it will be moving across the GLUT2 channels to enter the interstitium, then it will be picked up by the capillaries, and then the capillaries will join to form the hepatic portal vein, and the hepatic portal vein will transport whatever has been absorbed here to the liver for further metabolism and storage of these molecules. But remember, we say that the sodium glucose transporter 1, it's only transporting glucose and galactose. But what about fructose? Fructose, there's another channel that will facilitate movement of fructose. So we have the GLUT5 channel. So the GLUT5 channel is the one that is responsible to internalize fructose. So fructose will move via the GLUT5 channel into the enterocytes, then it will move via the GLUT2 channel into the interstitium. But on top of that, we also have other channels that can allow movement of fructose on the basolateral side of the membrane into the interstitium, but these transporter proteins, they are not known, okay? So they are not well understood, but we just know that they are there and they are responsible for movement of fructose. So this is their overall absorption of carbohydrate monomers. But you need to know that for you to transport sodium and glucose and galactose, you need to reduce the concentration of sodium within the cells, because as the cells are internalizing this sodium, if the concentration of sodium builds up within the enterocytes, it will be very difficult for sodium glucose transporter protein to push these substances into the cell because the concentration is already high within the cell. So on the basolateral side of the membrane, we have sodium, potassium co-transporter. So not co-transporter, but antipodes. So these are sodium, potassium ATPase antipode. So you know to say they are going to be transporting 3 sodium from the cell to the outside and 2 potassium from outside into the cell. So the concentration of sodium now will be reducing within the enterocytes. That will create the concentration gradient. So this concentration gradient now will favor the movement of sodium from outside, which is from the lumen of the GIT into the enterocytes. As the sodium is moving down the concentration gradient, it will move with it another molecule, be it glucose or galactose. So the movement of glucose and galactose against the concentration gradient is facilitated by the energy that is derived from the movement of sodium that is moving down the concentration gradient. So that's the internalization of carbohydrates, okay? So even this diagram is just the same information, but you have the same glucose, galactose that are using sodium glucose co-transporter. So this is a secondary active transport. Then for fructose, we said it's moving via the GLUT5 channel. So the GLUT5 channel is facilitated diffusion of fructose into the cells. Once they move into the enterocytes, they will move across the GLUT2 channel. So you can see the GLUT2 channel. There's a hand. Let me just activate your mic so that you are able to say. So there's a hand. Okay, your mic is active. You can go ahead. I don't know whether you have a question or what. Okay, that student is not saying anything. We continue. So now you have the glucose, galactose, and fructose within the enterocytes. They'll be moving across the group 2 channels into the interstitium, and then they'll move across the pores of the capillaries into the capillaries, and then they'll be transported by hepatic portal vein to the liver. Then we say that once some of these nutrients are transported to the liver, then they'll be converted into glycogen and stored within the liver. They'll also be transported to the other cells that they will need glucose, galactose, and fructose for metabolism. Then we say the concentration of sodium is created because of the sodium potassium ATPase pump. So the sodium ATPase pump is going to pump 3 sodium to the outside into the interstitium and 2 potassium into the cells. So the concentration will be reducing within the enterocytes. That will enhance the function of sodium, glucose co-transporter proteins for the internalization of glucose and galactose. Okay, that's enough for the carbohydrates absorption. The processes are the same even in this diagram that you are seeing here. But let's move on to proteins. So proteins, digestion and absorption of proteins, maybe within 5 minutes as well. So the characteristics of proteins are a sequence of amino acids attached by peptide bonds. So you have a chain of amino acids, which is called polypeptide chain. So you have a lot of amino acids attaching to one another using the peptide bonds. So in the stomach, that's where you have the initial digestion of proteins because we have pepsin in there. The pepsin is activated at the pH of 2 to 3 or 1.5 to 3 if you want. So once this pepsin is activated, it will break down proteins. So it will work on collagen as well. Collagen is a special type of protein. So it will be worked on by pepsin into smaller amino acids and smaller polypeptides. So you have smaller polypeptide and amino acids as a byproduct of digestion of collagen. So in the small intestines, after gastric empty, so now the chyme has moved into the small intestines. In the small intestines, there are a lot of enzymes that are coming from the pancreas that are responsible for protein digestion. So we have trypsin. We say that trypsin is being produced as trypsinogen, and then it will be activated by enterokinase, which is also called enteropeptidase. So it's going to activate trypsinogen into trypsin. So the enterokinase is an example of brush border enzyme. So the activation of trypsin is taking place within the duodenum. So we have the activation of trypsinogen into trypsin. Then the trypsin will start activating other enzymes. Remember, you have the chymotrypsinogen that will be converted into chymotrypsin. So the trypsin and the chymotrypsin will break down proteins into smaller polymers. Carboxylpeptidase is going to remove amino acids from these proteins. So from the carboxyl end of the protein. So you have the carboxylpeptidase. Then we also have elastase. Elastase are responsible to digest elastin fibers. So you have elastin fibers that are being digested by elastase. All these enzymes, they are coming from the pancreas. So they are part of pancreatic secretions. So a few proteins break down the amino acids by pancreatic secretions. The final products, we are going to have di and tripeptides that will be worked on by brush border enzymes. So the di and tripeptides will be worked on by the brush border enzymes to convert them into amino acids. So the enterocytes, they are going to have a lot of brush border enzymes. So these will include aminopeptidase and dipeptidase that will finish up now the digestion. So they will split the polypeptides to amino acids and those that are absorbed in di and tri form. Okay, so they are going to be broken down. So within the cytosol again, you also have the aminopeptidase and dipeptidase that can also continue the digestion of proteins within the cytosol of the enterocytes. So the proteins are absorbed as amino acids into the blood. Okay, absorption of amino acids. So this is just a summary of digestion of proteins. So in the stomach, pepsinogen, we say that to be converted into pepsin by hydrochloric acid. Then the pepsin will start the digestion of proteins into smaller proteins like peptones and proteases. So these are smaller form of proteins. So they are smaller polypeptides. Then in the small intestines, this is where the trypsinogen is being worked on by enterokinase to activate it into trypsin. Then the trypsin will start activating other enzymes like chymotrypsinogen into chymotrypsin, procarboxypeptidase into carboxypeptidase. Then you have these enzymes that will continue working on the proteins. And then the last enzymes that will work on these proteins are the brush border enzymes. So you can see the brush border enzymes that will finish the digestion. So they work on dipeptides into amino acids. So these are called dipeptidase that are working on the dipeptides. So these are brush border enzymes that will finish now the digestion of proteins, then they need to be absorbed. Absorption of amino acids is similar to that of carbohydrates. So you can see in the lumen here, you have the brush border enzyme that will finish the digestion of the proteins. Then you have the channels that are responsible for absorption of amino acids. So these are called amino acids, sodium co-transporter proteins. So just like we had sodium glucose co-transporter protein, even here we have sodium amino acids co-transporter proteins on the apical side of the enterocytes. So the movement of these amino acids is facilitated by the movement of a sodium. So it's an example of secondary active transport. So the absorption of glucose, galactose, and amino acids, it's using secondary active transport. So they require a lot of electrolytes, which is sodium. So that's why from intestinal secretions, pancreatic secretions, the liver secretions, which is part of gall or maybe bowel. So bowel contains a lot of electrolytes. So these secretions, they contain a lot of electrolytes because you need some of these electrolytes for absorption to take place. So for you to absorb glucose, for instance, you need a lot of electrolytes. So that's why in ORS, you have the fluids, the glucose, and also electrolytes like sodium chloride. So they add a bit of salt there because you need the sodium to help the absorption of glucose and other carbohydrate monomers. So even amino acids, for absorption to take place, you need electrolytes like sodium because they're using sodium amino acids co-transporter. Then on the basolateral side of the membrane, you also have the carrier proteins, which are just facilitating the movement of amino acids. So on the basolateral side, you have facilitated diffusion kind of movement. Then these amino acids are entering the interstitium, then they'll be picked up by the capillaries, then the capillaries will join to form the hepatic portal vein to transport the amino acids to the liver, to the hepatocytes, for storage and for other metabolism to take place there. Okay. Moving on to fats. So the dietary lipids are primarily 90% triglycerides. So you have triglycerols or triglycerides, which are 90% of the fats that you are eating. But also we have a bit of cholesterol esters, phospholipids, and essential unsaturated fatty acids, and also fat-soluble vitamins as part of fat. So fat-soluble vitamins like ADEK, vitamin A, D, E, K. So this will be absorbed together with fat because it's fat-soluble. So just not to say when you talk about fat digestion, you think of triglycerides, you think of cholesterol esters, phospholipids, unsaturated fatty acids, and also fat-soluble vitamins, which are vitamin A, D, E, K. So these 4 vitamins are absorbed together with fat. So essentially all 98% of fat consumed in the diet is absorbed and most is transported to adipose tissue for storage. So 98% of the fat that you are eating after absorption, it will be transported to the adipose tissue for storage. Maybe you're just using 2% of it. The other percentage will be stored within the adipose tissue. So it will be transported to the adipose tissue for storage. But the same free fatty acids can be converted into carbohydrates. If the body needs a lot of carbohydrates and then you don't have it, most of these free fatty acids or fat tissue can be converted into carbohydrates for the body to use it. Digestion is taking place in the mouth. In the mouth, there's a bit of lingual lipase that will break down 10% of fat. So lingual lipase. In the saliva, there is also production of lingual lipase that is responsible for 10% of fat digestion in the oral cavity. So the lingual lipase followed by gastric lipase. Remember the chief cells, we said they were producing pepsinogen and gastric lipase. So even in the stomach, there's a bit of lipase that is being produced there that is responsible for minor digestion of triglycerides. So just minor digestion, it's not a major digestion. So removal, and also remove one of the 3 fatty acids, leaving diglycerol and also free fatty acid as a product. So what I mean is the lingual lipase and gastric lipase, they are just removing one of the 3 fatty acids. So they will just break down the triglycerides into diglycerides and 1 free fatty acid. That will be the products. So if you have triglycerol, it will be broken down into fatty acid and diglycerol by the lingual and gastric lipase. That's what it means. Then from there, the chyme will be emptied into the duodenum. That's where major digestion of fat is taking place. Why? It's because for digestion of fat to take place, you need emulsification process to take place. So the bile salts, the phospholipids, they are responsible for emulsification of fat. So the emulsification will made it possible by bile salts. So remember, bile salts and phospholipids are the ones that are responsible for emulsification because they have a polar and non-polar ends. So they are antipathic to some extent. They are antipathic because they have fat-soluble domain and water-soluble domain, or hydrophobic and hydrophobic domain that will be able now to emulsify the fat. So the polar ends are soluble in water and mix with it, while the non-polar dissolves with the fat. So you have one end that is interacting with water and another end that is interacting with the fat. So it will be able to emulsify the fat, exposing the surfaces that can be worked on by a lipase. So a lipase requires that the fat globule should be emulsified into fat droplets. And these fat droplets, they will be exposing the sites now where the enzyme is going to work on. So we have the bile salts in the duodenum that you emulsify large fat globules. So this is a physical breakdown of fat globules into smaller fat droplets. So the digestion of fat by the pancreatic enzyme lipase yields 3 fatty acids and monoglycerides. And these then associate with the bile salts to form the micelles or the micelles. So they'll form the micelles, which ferry them to the intestinal mucosa, which will transport them now to the intestinal mucosa. So after the digestion of fat, they'll be converted into micelles, and the micelles will be now transported to the intestinal mucosa for absorption to take place. Okay, so a lipase is water-soluble enzyme. So for it to digest it, it means that you need emulsification process. So emulsification is imperative for complete digestion of fat. Why? It's because the lipase, which is fat-soluble, it can't enter the fat globule. So that fat globule has to be broken down into smaller droplets, increasing the water fat interface. So if you increase the water fat interface, then the lipase will be able to work on those fat droplets. So both pancreatic and enteric lipase, they will split the fat into free fatty acids and 2 monoglycerides. So these need to be ferried into the cell as quickly as possible, as they can easily bind to form fat again. So once you have digestion of fat, fat has got a tendency to reaggregate. So you can have reaggregation of fat, then it will be converted into a fat globule again. So to prevent that, they need to be transported in form of micelles to the mucosa that is responsible for absorption of fat. So the bile salts form micelles by binding to these monomers and ferrying them to the cells. So they'll be carried to the cells. So at the brush border of the epithelium, the fat monomers are absorbed as they are lipid soluble, and bile salts return to the chyme in the intestines. So after the bile salts they have done their work, they will return to the intestine to emulsify more fat. But now the free fatty acids, the glycerol molecules, you know, to say that these are fat soluble, so they can easily cross the phospholipid bilayer without using any channels. So there are no channels for absorption of fat. So once there is fat absorption, when they are transported to the mucosa, they can easily cross the phospholipid bilayer of these cells to enter the cells. So they will be absorbed by simple diffusion, if you want. So the steps that are involved in fat digestion. So the major digestion of all lipids occur in the lumen or the small intestines. This is where major digestion of fat is taking place. The pancreatic lipase will remove the fatty acids from the carbon one, so carbon number one. So the pancreatic lipase will just remove a fatty acid from carbon number one and carbon number three. So it will be converted into two fatty acids and monoglycerides. But this activity requires a co-lipase. So we have a coenzyme or a co-lipase that will activate the pancreatic lipase. So for the pancreatic lipase to be active, it requires a co-lipase, which is a small protein that will increase its activity. Then the cholesterol they will remove the ester portion of dietary cholesterol ester to facilitate its uptake. Okay, so cholesterol esters, they are being broken down into cholesterol and esters by the cholesterol esterase. That's the enzyme that is breaking down that. And the phospholipids, we have phospholipase A2. The phospholipase A2 is the one that will break down the phospholipids. So the phospholipase A2 removes a fatty acid from carbon number 2 of the glycerol backbone, leaving a fatty acid on carbon number 1 and the polar head group on carbon number 3. This is referred to as lysophospholipids. So lysophospholipids. So down here are equations of digestion that is taking place and the enzymes that are responsible for this digestion. So the pancreatic lipase is responsible to break down triglycerides or triglycerol into two fatty acids and monoacylglycerol. Then we have the cholesterol esterase that will break down the cholesterol ester into cholesterol and ester. Then we have the phospholipids that are being broken down by phospholipase A2 into fatty acid and lysophospholipids or lysophosphoglycerides. So these are the digestion of fat. So after fat has been digested by pancreatic lipase, so you can see the triglycerides on one end here as a substrate. So we have triglycerol or triglyceride that will be worked on by pancreatic lipase within the lumen of the intestine. Then this pancreatic lipase can remove fatty acids from carbon number 3. So you can see from carbon number 3, one fatty acid has been removed. Then the same pancreatic lipase will work on the diglycerol to remove another fatty acid on carbon number 1. So you can see on carbon number 1, the fatty acid has been removed. Then what will remain with is two monoacylglycerol. So the two monoacylglycerol, it means that you have the glycerol molecule with one fatty acid that is attached on carbon number 2. Hence the name two monoacylglycerol molecule. Then here you need an isomerase. The isomerase is going to remove this acyl group or the fatty acid from carbon number 2 to carbon number 1. So you can see there is movement of this fatty acid from carbon number 3 to carbon number 1. So once you move the fatty acid to carbon number 1, then another pancreatic lipase will work on it to remove this the fatty acid on carbon number 1, so that now the products are converted into fatty acids with the glycerol molecule. So these now, they'll be combined with bile salts and phospholipids for the formation of micelles, and they'll be transported to the mucosa cells. Like I said, to say phospholipids, they are fatty soluble, so you don't need channels for them to move. So they'll be just absorbed. They will move across the phospholipid bilayer to enter the cells. Then they'll be picked up by the rough endoplasmic reticulum. There will be aggregation of free fatty acids and the glycerol molecule for the formation of the triglycerides again within the mucosal cells. Then here now, this is where there will be addition of lipoproteins. So they will be added to lipoproteins. Then those lipoproteins will be converted into chyromicrons. So the chyromicrons now will be exocytosed, and then they'll be picked up by the lacteals. Then they'll be transported by the lymphatic system. Okay, so the micelles, they'll carry the fat globules to the epithelium. So you have soluble fat that will enter the cells, and the monomers are taken up by endoplasmic reticulum to form new triglycerides, like I explained. So within the enterocytes, after absorption of free fatty acids, glycerol molecule, they'll be taken up by endoplasmic reticulum for the formation of triglycerides. So they'll aggregate again within the endoplasmic reticulum to form triglycerides. And these triglycerides will be converted into chyromicrons now by the addition of lipoprotein. And these chyromicrons will be now packaged into vesicles, and they will be transported to the other side of the cells. And then there will be exocytosis of chyromicrons that will be picked up by the lacteals. So you can see here within these finger-like projections at the center, we have the lacteal, which are more like opening up of lymphatic vessels that will internalize the chyromicrons, and then they'll be transported back to the cardiovascular system. Okay. So that would be the transportation of the lipids after absorption. So like I said, the digestion of lipids is taking place at lipid-water interface. So at lipid-water interface, this is where the lipase will work on. That's why you need emulsification to take place. So we have the bile salts and the phospholipids, which are antipathic in nature. So they will act as detergents to emulsify the lipid droplets so that they are now smaller enough, increasing the surface area or increasing the interface where the enzymes will be able to go and digest them into triglycerides, glycerol molecules, and then it will be internalized by the mucosal cells. It will be picked up by the endoplasmic reticulum. So the uptake of triglyceride, the uptake of fatty acids and also triglycerol by the endoplasmic reticulum. There, they will aggregate to form triglycerides. Then they'll be packaged into vesicles, which are called chyromicrons, addition of lipoproteins, then exocytosis, then they'll be taken up by the lacteals, transported back to the cardiovascular system. So absorption of fat, we say that it's just via simple diffusion. So you have passive diffusion process because they are fat soluble. So the two monoglycerides, fatty acids, lysophosphodiesterase, free cholesterol, they will form micelles. So in micelles, you have a combination of phospholipids and a bit of bile salts and these molecules that are coming from fat digestion. Then they'll be transported to the enterocytes for absorption. So you can see now the fatty acids, the monoglycerides, they will move across the apical side of the membrane to enter. Then it will be picked up by endoplasmic reticulum. Then they will aggregate within the endoplasmic reticulum to form triglycerides. Then these now will be packaged into vesicles, which are called chyromicrons. The chyromicrons will be exocytosed on the basolateral side. Then you know to say that the chyromicrons will be picked up by the lacteals, which are part of the lymphatic vessels. So you have these lymphatic vessels that are responsible for absorption. Okay. I think this is just the same information. So for now, you just need to know that in circulation now you have lipoproteins. So remember, we have high density lipoprotein and low density lipoprotein, of which in biochemistry we are taught that the high density lipoprotein, they are good, the low density lipoprotein, they are not good. Why? It's because The low density lipoprotein, they contain a lot of cholesterol. So it's the one that will be depositing cholesterol in the blood vessels, which is not good because it can result into hardening of blood vessels or stiffening of blood vessels. So you don't need a lot of low density lipoprotein. That's why the liver is also responsible for internalization of low density lipoprotein for the production of bile. So a lot of bile acids, they are being produced from low density lipoprotein. So the cholesterol in the low density lipoprotein will be broken down, then it will form bile that is required for the emulsification processes of fats. Then the other form of digestion, due to time, this is where we're going to end our class for today, unless if there are questions.